Do you live in Indonesia? Do you have family or friends anywhere on the island of Sulawesi? In Palu, in Sigi, in Donggala, or in any of the coastal communities stretching along the shores of Palu Bay? If the answer is yes, or if you care about what is unfolding right now in one of the most geologically dangerous places on the face of this earth, you need to watch this entire video. Because what happened today, on June 16th of 2026, is not just another earthquake statistic, it is a signal. And the people who understand what that signal means are genuinely alarmed. This morning at 11:27 local time in Central Sulawesi, the ground beneath the city of Palu shook with a magnitude 7 earthquake. That is a powerful, destructive earthquake by any standard. The epicenter was located 43 kilometers east-southeast of Palu, at a depth of only 10 kilometers. Those two numbers together, the location and that shallow depth, are what make this event so dangerous, so immediately concerning, and so deeply connected to one of the worst natural disasters in modern Indonesian history. Within 3 minutes of the main shock, a magnitude 5. 2 aftershocks struck, then a 5, 0, then a 4, 9. By the time this script was written, at least 55 aftershocks above magnitude. 2. 0 had been recorded in the area, and the sequence was still ongoing. Residents of Palu, a city of 400,000 people in the capital of Central Sulawesi province, fled into open streets. Patients in hospitals, some still attached to IV drips, were carried or walked outside by medical staff making impossible decisions in terrifying moments. But here's the problem. This is not just a powerful earthquake near a city. This is a powerful earthquake on one of the most notorious fault systems on the planet. The Palu-Koro Fault runs directly beneath this region, and the last time it fully unleashed, it did something that scientists had never seen before in a place like this, something that still haunts seismologists, something that the ground beneath Palu may be capable of doing again. To understand why today's earthquake has geologists watching their monitors with cold unease, you have to go back to September 28, 2018. That was the day the Palu-Koro Fault produced a magnitude 5 earthquake, one that did not just shake the ground, but broke the fundamental laws of how earthquakes are supposed to behave. Scientists who studied that event afterward used language rarely heard in the dry literature of seismology. They called it a supershear earthquake, and that word carries weight that most people have never been asked to carry. Here is what supershear means and why it matters so much right now. Every earthquake produces two kinds of seismic waves. The faster waves, called primary or P waves, compress and expand the rock as they travel through it. The slower waves, called shear or S waves, move the ground sideways, up and down, in the lurching, violent motion that actually topples buildings. For virtually every earthquake that has ever occurred, the fault rupture itself, the physical tearing of rock along the fault line, travels at a speed below those shear waves. That is the natural speed limit, set by the physics of how rock fractures and how energy propagates through the earth. In 2018, the Palu-Koro Fault broke that speed limit. The rupture tore through the crust at somewhere between 4, 1, and 5. 3 kilometers per second. The shear wave speed in that region is approximately 4 to 3, 8 kilometers per second. What this means is the fault rupture was traveling faster than its own shear waves, and the consequences of that are terrifying in ways that took scientists time to fully process. When a rupture moves faster than shear waves, those waves begin to pile up behind the rupture front, stacking on top of each other the way a sonic boom piles sound waves in front of a supersonic jet. The result is a concentrated shock front, a wall of seismic energy that slams into whatever it meets with amplified, intensified force. Ground shaking from a supershear earthquake is not just stronger. It is fundamentally different in character. It hits harder, faster, and from unexpected directions. This next part matters because it explains something that baffled engineers and scientists after the 2018 disaster. Why did the tsunami at Palu happen at all? The 2018 earthquake was a strike-slip fault rupture. In that type of earthquake, the two sides of the fault slide horizontally past each other, like two hands rubbing together. Strike-slip earthquakes are not typically associated with major tsunamis. They do not generally thrust the seafloor upward or downward in the way that creates the massive wave displacements we associate with events like the 2004 Indian Ocean disaster. And yet, in 2018, tsunami waves reaching heights of 18 to 20 feet swept through Palu Bay and killed thousands. For years, the scientific community wrestled with why. Part of the answer, researchers discovered, lies in the supershear nature of the rupture itself. The shock front generated by the supersonic fault tearing may have contributed directly to underwater landslides and seafloor deformation along Palu Bay, generating waves that no warning system was designed to anticipate. The bay's narrow funnel shape, the same geography that makes Palu beautiful, amplified those waves further. And by the time anyone understood what was happening, it was too late. The final death toll from September 28, 2018 was 440 people killed, More than 2,141 of those deaths occurred in Palu alone. Over 1,000 bodies were never identified. Another 667 people remain missing to this day. More than 70,000 houses were destroyed. More than 42,000 structures of all kinds suffered some form of damage. It was the deadliest natural disaster anywhere on Earth in 2018. And now, on June 16, 2026, exactly 8 years and 3 months later, a magnitude 6.7 earthquake has struck 43 kilometers from that same city, on the same fault system, at the same shallow depth of 10 kilometers. But that is not the real story. The real story is what this earthquake may represent in the larger context of stress loading on the Palu-Koro Fault, and what that means for what could still come. Here's what we know about this fault. The Palu-Koro Fault is a left lateral strike-slip fault running approximately 220 kilometers through Central Sulawesi. It is one of the fastest moving strike-slip faults on Earth, accumulating strain at a rate that geology books struggle to convey in casual terms. Sulawesi sits at the triple junction where the Pacific, Australian, and Eurasian tectonic plates all converge. The pressure these plates exert on the island's interior is enormous and constant, and the Palu-Koro Fault is the geological release valve, the seam in the crust where all of that pressure eventually has to go somewhere. Historical records show that destructive earthquakes on this fault stretch back at least to 1905, with significant events also in 1907, 1934, 1968, 1998, and 2018. That 2018 event was classified as the strongest to strike this part of Indonesia in the modern era. Today's 6.7 is now the strongest earthquake to affect this region in over 8 years. Most people are missing this. They are looking at today's event and seeing 6.7 magnitude, 8 injured, scattered damage, no tsunami. And on its own, that would be a manageable story. But geologists are not looking at today's event in isolation. They are looking at where that 6.7 earthquake occurred at 10 kilometers depth on the same fault complex that produced the supershear catastrophe of 2018. And they are asking a question that does not yet have a comfortable answer. Was this a standalone event, or is the Palu-Koro Fault reloading? Let us talk about what happened in Palu today, because real peoples are living through this right now and their stories deserve to be told. When the ground began shaking at 11:27 this morning, the shaking lasted for more than a full minute in Palu City. 60 seconds of violent, lurching, relentless motion. Palu resident Muhtar Ahmad described it as extremely strong. That description came from a man who has lived through earthquakes his entire life in one of the most seismically active cities on Earth. When someone like that calls a shake extremely strong, that is not casual language. Hospitals in the city immediately evacuated. At Anuddhapura General Hospital, medical staff made the decision to move patients outside, some still connected to drips and monitors, setting up what was effectively a field ward on the hospital grounds while the building was assessed for damage. That is the kind of scene that happens when a hospital's engineering staff looks at the shaking their building just endured and makes the call that the inside is not safe. In the regency of Sigi, just southeast of Palu and closer to the epicenter, at least 8 people were rushed to hospital, including 2 with serious injuries. And here's the number that should stop everyone. 3 regencies close to the epicenter, Sigi, Poso, and Donggala, with a combined population of 1. 2 million people had not been fully assessed as of the time of this report. Roads linking Palu to neighboring regencies were damaged or cut. A section of provincial road connecting Palu to both Sigi and Poso was severed. 2 bridges were damaged. The National Disaster Management Agency confirmed destruction of 64 houses, 4 places of worship, 4 public facilities, 2 government office buildings, a cafe, and a hotel, with the hotel manager making the decision to evacuate all guests immediately. And now it gets worse. Because while Indonesia's Meteorology, Climatology, and Geophysical Agency, the BMKG, issued a statement saying there was no danger of a tsunami from today's event, they also issued a second statement that is receiving far less attention. Aftershocks could continue for hours, possibly days, and residents should remain vigilant. That second statement is the one that matters for people in Palu Bay communities tonight. Here is why. The BMKG's simulation found today's earthquake would not trigger a tsunami. That simulation was based on the initial fault parameters, the location, depth, and rupture geometry of the 6.7 main shock. But aftershock sequences are not predictable in their full scope. The 55 aftershocks already detected today include events at magnitude 5, 2, 5, 0, and 4, 9. These are not small tremors. A 5, 2 is a strong earthquake in its own right. And the concern that seismologists who specialize in fault aftershock sequences will tell you is always present after a major strike-slip event on a complex fault, is that larger aftershocks can occur hours or even days after the main shock. In some sequences, what looks like the main shock turns out to be a foreshock. The scientific record of the Palu-Koro Fault is instructive here. On September 28, 2018, the sequence began not with the magnitude 7.5 event, but with a magnitude 6, one foreshock that struck earlier in the day. People felt that foreshock. Some moved away from the coast, others returned home. Then, hours later, the magnitude 7.5 arrived, and within minutes, tsunami waves were sweeping through Palu Bay. Now the focus shifts to a deeper technical concern that has been building in the scientific literature for years since that 2018 disaster. The question of what the rest of the Palu-Koro Fault looks like today. The 2018 earthquake did not rupture the entire 220-kilometer length of the fault. Seismic analysis showed that the rupture propagated southward from its nucleation point for approximately 150 kilometers, traveling at those extraordinary supershear velocities. The northern segments of the fault, which seismologists call the Donggala segment, may not have fully released. And to the south, additional segments exist that scientists have been monitoring with increasing concern since 2018. When a large earthquake ruptures part of a fault, it redistributes stress. Some portions of the fault may be relieved. Others are loaded further, pushed closer to their own failure threshold by the forces that arrived when the neighboring segment let go. This is called stress transfer, and it is one of the most frustrating aspects of earthquake science. You can calculate where stress has been added, but you cannot calculate exactly when the affected portion will rupture or how large that rupture will be. What today's magnitude 6.7 event tells us is that stress on the Palu-Koro Fault system remains high. The region is not quiet, it is active. It produced more earthquakes today, 276 in total across Indonesia, with Sulawesi generating the strongest of all of them. This is where it becomes dangerous. The broader context of Indonesian seismicity this year makes today's event even more alarming when viewed from altitude. Earlier this year, on April 2nd, 2026, a magnitude 7.4 earthquake struck 126 kilometers west-northwest of Ternate, in Indonesia's northern Molucca Sea. That event was the strongest in the country in over a year, and it triggered tsunami waves in 5 locations, with the highest measuring 75 meters in North Minahasa in North Sulawesi. That is only a few hundred kilometers from today's epicenter. Indonesia's seismic arc is activating across multiple points simultaneously. Indonesia's own historical statistics tell the deeper story. Based on data going back to 1900, the country records approximately 12,000 earthquakes per year. Of those, about 7,200 are magnitude 3, 0 or higher. About 2,500 are magnitude 4, 0 or higher. And approximately every 5 to 10 years, Indonesia sees a magnitude 8, 0 or above. Since 1900, there have been at least 18 such events, the last magnitude 7.9 struck in January 2023. The mathematical reality is this. Indonesia is overdue for the next major event. And the Palu-Koro Fault, with its documented capacity for supershear rupture, its proximity to a vulnerable bay city of 400,000 people, and its history of producing the most destructive disaster Indonesia has seen in modern times. This fault is not a background concern. It is the front line. Now, the question of warning systems. One of the most painful legacies of the 2018 disaster is what it revealed about Indonesia's tsunami early warning system. At the time of that earthquake, the country had a network of deep ocean buoys designed to detect tsunami waves early enough to give coastal residents time to evacuate. But in the months and years before September 28, 2018, many of those buoys had gone offline. Some were vandalized, some suffered technical failures. The monitoring system was degraded at the exact moment it was most needed. After the disaster, Indonesia pledged a major overhaul of its warning infrastructure. New buoys were ordered. Communication protocols were redesigned, community alert systems were strengthened, and to BMKG's credit, this morning's magnitude 6.7 event was assessed quickly, and an initial determination, no tsunami danger, was communicated to the public within minutes. That is a real improvement. But improvement and adequacy are not the same thing. The 2018 tsunami, the one that scientists are still writing papers trying to fully understand, did not behave in a way that any conventional warning model predicted. It was generated partly by a type of fault motion, supershear, strike-slip, that the existing models were not built to handle. Residents who received the 2018 tsunami warning, such as it was, had only minutes between that warning and the arrival of the first wave. Some estimates put the interval at 8 minutes. In a city of 400,000 people with narrow coastal streets, blocked evacuation routes, and a bay that funneled incoming energy like a lens, 8 minutes is not enough. And tonight, the residents of Palu, Donggala, Sigi, and the communities along the shores of Palu Bay are sleeping with that knowledge. Many of them survived 2018. Many of them lost family members in 2018. Many of them looked at the sky when the ground stopped shaking this morning and instinctively moved away from the coast. not because they received an official warning, but because their bodies remember what happened the last time the Palu-Koro Fault broke. One hotel manager evacuated his entire building before official guidance arrived. Hospitals moved their patients outside before the aftershock sequence peaked. Ordinary citizens ran to open ground before any announcement told them to. This is what trauma memory looks like at a community level. It is also a form of resilience, a hard one, devastating in origin, but real. What happened next changed everything in our understanding of this fault, because after 2018, researchers went back and looked at historical records of earthquakes on the Palu-Koro system. They found something sobering. This fault has been producing large earthquakes with remarkable regularity for at least 120 years. The 1905, 1907, and 1934 events. The 1968 event, also a magnitude 6. 7, the exact same magnitude as today's earthquake. The 1998 events, a pair of 6, 7, and 6. 0 magnitude quakes. Then 2005, 2012, and 2018. Do you see the pattern? A magnitude 6, 7 on this fault system is not an anomaly. It is a recurring character in this fault's history. The 1968 event was a 6, 7. Today is a 6, 7. This fault has been producing earthquakes of this energy level across decades. And each time it does, it raises a question that seismologists cannot fully answer in advance. Is this the end of the sequence, or the beginning of something larger? One more thing you need to know. The town of Sigi, one of the regencies closest to today's epicenter, sits in the same valley corridor as the 2018 rupture zone. In 2018, 3 villages in the Sigi area, Balaroa, Petobo, and Jono-Oge, experienced something beyond the earthquake and tsunami. They experienced liquefaction, a phenomenon where saturated soil behaves like a liquid, swallowing buildings, roads, and people with a slow, relentless momentum that rescue teams described as unlike anything they had encountered. Hundreds of people died in those 3 villages from liquefaction alone. Some were never found. The soil conditions in the Palu Valley that made liquefaction possible in 2018 have not fundamentally changed. The flat alluvial deposits along the valley floor, the same geological material that cities and towns are built upon, remain susceptible to losing their structural integrity when subjected to prolonged, intense shaking. Today's earthquake shook Palu for more than a minute. That duration at the magnitudes reported is well within the range that can begin to mobilize saturated soils. The National Disaster Management Agency is still collecting damage reports. The 3 regencies with a combined population of 1. 2 million have not been fully assessed. Road links are cut. Aftershocks at magnitude 5. 0 and above have continued. And the question of what the soil in the valley looks like tonight, whether the water table in the rice paddies and alluvial plains around Sigi is saturated, whether today's shaking has disturbed the structural cohesion of material that once swallowed entire neighborhoods. That question does not have an answer yet. Let us be precise about the geological threat this region represents at this moment. The Palu-Koro Fault moves at rates that geologists estimate between 35 and 45 millimeters per year. In geological time, that is extremely fast for a continental strike-slip fault. It means the fault is not slowly and gently creeping. It is locked, building stress, and releasing it in sudden, catastrophic bursts. The 2018 earthquake released an enormous amount of that accumulated stress, but an 8-year interval for a fault moving at 40 millimeters per year means approximately 320 millimeters of accumulated strain since that event. On a fault that previously produced supershear ruptures, that number is not academic. It is structural reality. Geophysicists who study the region have mapped several fault segments along the Palu-Koro system that have not ruptured in the historical record. The Donggala segment to the north of Palu, additional branches to the south and east. These are described in peer-reviewed literature as having high asperities, rough locked patches that store elastic energy until they cannot anymore. The 2018 rupture may have loaded some of these segments further. Today's 6, 7 may have done the same. This is where the science becomes genuinely frightening, not in a theatrical way, but in the way that careful, meticulous scientists speaking plainly about data become frightening. Because what the record shows, the 1905 earthquake, the 1907, the 1934, the 1968, the 1998, the 2018, is a fault that does not rest. It charges. It holds. And it releases in ways that science is still working to fully understand. Tonight, families in Palu are outside their homes. Some because official guidance says buildings should be assessed before reoccupation. Some because they simply cannot bring themselves to go back inside after what the earth did this morning. Children who were too young in 2018 to remember what happened are watching their parents' faces for information the parents themselves do not have. Elderly residents who survived the tsunami 8 years ago are sitting in open courtyards, listening for sounds in the earth that have no scientific basis to warn them, but that feel necessary anyway. Across the bay, in the fishing communities along the coast, boats have been pulled further from the waterline. It is not an official instruction. It is memory, operating faster than data. The Indonesian National Search and Rescue Agency has teams moving towards Sigi, the area with confirmed injuries. 2 people are described as seriously injured, but the full extent of damage to the 64 houses, 4 worship sites, 2 bridges, 2 government buildings, and the road infrastructure that connects a regional capital to its surrounding population of 2 million. That assessment will take time. And time in an active aftershock sequence on the Palu-Koro Fault is not a neutral quantity. The BMKG has confirmed that aftershocks can continue for hours. What they cannot confirm is their magnitude ceiling. In sequences following large earthquakes, statistics favor diminishing aftershocks. But statistics are not guarantees. The Moriutsu law of aftershock decay has been surprised before. The 2018 earthquake itself was preceded by a foreshock. Scientists do not yet have the tools to reliably distinguish in real time between a main shock and a foreshock. What is beyond dispute is this: the Palu-Koro Fault is awake today. It produced 276 earthquakes across Indonesia in the past 24 hours, with Sulawesi generating the strongest of all of them. The strongest aftershock alone, magnitude 5. 2 was powerful enough to be felt across the region. The sequence is still active. The road to Sigi is cut. Assessment teams are still moving toward the most affected areas. And somewhere beneath the alluvial plains of the Palu Valley, beneath the bay that channeled 20-foot waves in 2018, beneath the city of 400,000 people who woke up this morning to the sound of their walls cracking and their world shaking, the fault continues to move. Slowly, relentlessly, building towards something that may be a minor aftershock or may be the beginning of the next chapter in the most geologically violent fault story in modern Indonesian history. The scientists who have dedicated their careers to understanding the 2018 supershear rupture, the earthquake that broke the geological speed limit that produced a tsunami from a strike-slip fault, that killed 340 people and changed the way seismologists think about what is possible. Those scientists are watching their data streams tonight. The people of Palu are watching the sky. The aftershock sequence continues, and what happens on this fault in the next 12 to 24 hours may tell us something we either desperately need to know or desperately do not want to learn.